introductory lecture organized by our Department of Mathematics at SHAHEED Bhagat Singh College. We stand before you today filled with anticipation and excitement for the forthcoming wave of knowledge and profound insights our distinguished guest will share. Without further delay, let us commence our day by lighting the lamps that will guide us through this enlightening session. I would like to request our valued guest and faculty member to illuminate these lamps. ओके यहाँ पे सर का नाम था
I have no idea.
I don't wish for you.
Okay. The blessings of the divine are a necessary precursor for a successful and mindful event. To infuse our day with light and wisdom, now I would like to invite the choir group to present a very soulful rendition of Saraswati Mantra.
या कुन्देन्दु तुषारहार धवला या शुभ्रवस्त्रावृता या वीणावरदण्डमण्डितकरा या श्वेतपद्मासना या ब्रह्माच्युत शंकर प्रभृतिभिः देवैः सदा वन्दिता सा मां पातु सरस्वती भगवती निशेष जाड्यापहा
Our heartfelt gratitude to the choir group for such a remarkable performance. The Department of Mathematics of Shaheed Bhagat Singh College holds a very prominent position as it is one of the leading departments of this college. And it started its journey in 1967, the very same year the college was established. The Department of Mathematics is a very I apologize for the discomfort. The Department of Mathematics holds a very important position as it offers the one and the only course of mathematical sciences in the field of mathematics. It is also a very important part of the Delhi University as it holds a very important position under the specially designed course of NEP UGCF. Now, let us proceed with a warm welcome. A heartwarming and mindful welcome is very important for the foundation of a successful session. I kindly request our respected teacher, Jyoti ma'am, to present a planter as a token of our gratitude to Professor R.K. Sharma, who will enlighten us with his profound wisdom and his knowledge.
Thank you, sir. Thank you, ma'am. Next, I invite respected Divya ma'am and Shweta ma'am to present a planter as a token of our deep appreciation to Mrs. Madhu Sharma, wife of Professor R.K. Sharma, for gracing us with her presence. Thank you, ma'am. Now, I would like to invite former senior faculty member Dr. Kulanand Sharma to impart his words of wisdom upon us.
Good morning, everyone. It's my pleasure to say a few words here. Actually, Sharmaji is not unknown to this college. He has been in this college earlier also, and he is a scientist, a mathematician, and overall a great humanitarian. I would like to say that he is not just a simple mathematician, but he has done pioneering work in his field, celestial mechanics. Sir, with your permission, I would like to say something. You can imagine that whenever you go for research work and whenever you think of doing some research in any area, you will go for searching the references in that field. But here is a person, one of his initial paper does not have any reference. He created the problem, he solved the problem, he took the solution to his teachers, and his teachers said that, what can we do here? Everything is done by you, so go and publish it. And he got it published. So it's a pioneering work in celestial mechanics. I cite one more thing. It happened that in one of the papers, in some papers, the other researchers used some terms at a wrong term, or we can say that a term not at appropriate place, and got their research done, published the work. Sharmaji noticed it and he corrected it, and he wrote a paper, went to the publishers to get it published so that the correct thing may be published. The publishers denied, say that don't get it published. Why? Because if this paper has been published, then the work done by the others till now will be a waste. So it is the caliber of Sharmaji that this kind of work is done by him. He has many research papers, more than 100 research papers, very good citation numbers, And at this age even, he is always ready to help the students. So I cannot say more than this. It's upon you to interact with him, to get benefited from here, and uh, all those who want to work in this field in celestial mechanics or space dynamics or related areas, he is so kind hearted that he is always available for that. So thank you.
Thank you, sir. With this, I would like to invite our teacher, Dr. Sandeep Kumar, to introduce our honorable chief guest, Dr. R.K. Sharma, and provide a deeper understanding of what lies ahead.
Thank you, Revans and Shivani. Before introducing our esteemed guest speaker first, I would like to welcome all present here. Professor R.K. Sharma worked in the Applied Mathematics Division at Vikram Sarabhai Space Center for 38 years, from June 1973 to June 2011. During this time, he served as the head of the division in as scientist G grade from November 2004 to June 30, 2011 at Vikram Sarabhai Space Center. Due to his excellent service, he received a 2-year service extension from the Government of India. After retirement from the Vikram Sarabhai Space Center, he joined Kruna University and worked as a professor in the Department of Aerospace Engineering uh, and worked as a professor in the Department of Aerospace Engineering at Kruna University, Coimbatore for 10 years. Professor Sharma is well known for his research in the field of celestial mechanics, orbital dynamics, interplanetary lunar trajectory analysis, Monte Carlo simulations, and reliability studies. He is a lifetime member of several societies, including the Aeronautical Society of India, System Society of India, and Indian Society of Theoretical and Applied Mechanics. Additionally, he is a member of the American Mathematical Society USA. He has authored over 100 papers published in referred international and national journals. His Google citation total is 1310. His H index is 17 and his I-10 index is 37. Professor Sharma has provided research guidance to more than 50 students at various levels of education. In recognition of his contribution, he received the ISRO Team Excellence Award in 2007 for the GSLV F-04 mission and the Best Researcher Award from the Kruna University in 2012, 2013 and 2014. Here, I would also like to mention that Sir has supported the college financially to start the Ruchi Sharma Memorial Award, an amount of 4,000 each year for the girl topper students. Dr. Ruchi was a professor of mathematics in UK. We are honored by your presence, sir. I request you, sir, to come and enrich our audience with your knowledge. Thank you, sir.
Mostly I used to be Thank you very much for the introduction you have given for me. Yeah, I got the opportunity to study at Delhi University, Ramjas College, from 1965 to 70. I did my BSc Honors Mathematics and then MSc in Mathematics. And then carried out my research in space dynamics. When in 73, I got opportunity to join Vikram Sarabhai Space Center, and by that time I already completed part of my research, and my guide said that you better join there and you can submit the PhD thesis from there. Are you able to hear me? Otherwise I'll come this little. So from 73, are you able to hear now? No. From 73, June 73 onwards, I was at Vikram Sarabhai Space Center, and in Applied Mathematics Division, we had a division, and that was the the imagination of, or the gift from Dr. Sarabhai. He said, without mathematics, there is no space research. Friends, this is very important. Such a great man, though he was a physicist, but his thought was that without mathematics, India cannot progress in space. That was the idea, and because of that only they formed this applied mathematics division. Still it exists there. I headed this for 7 years. After me, the person who headed, Dr. Anil Kumar, now he is a director of STRAC. All this tracking is done under his direction. And maybe he has another few years left. He may become director of one of the centers. A mathematician becoming director of a center is a very important thing. So mathematics is a thing which is a subject where you can reach any heights. Any heights you can reach. I have seen my boss, Dr. Adi Murthy, he has got a Padam Shri. And still we are working. We have completed one document on space debris. Whatever work has been carried out on space debris, we thought that it should not go waste. Then when I told him, he said, yes, we will write. So I, being the major contributor there, I have written 8 chapters. And one more chapter will be added by others, and it will be published by ISRO. We were not very much keen to get financial benefits, but then we were interested that the work which we have carried out should not go waste. Tomorrow, anybody wants to refer it, it should be available. So it will be a document which will be published by ISRO, and it will be available later on to everybody, because it may come in public domain also. So friends, this is a very important mathematics, because all of you are, I think, belong to mathematics. You should, wherever you go, you see mathematics has got number of areas where you can contribute is now increasing and increasing and increasing. At that time, since I was interested in space, so I went there. But I could have even contributed here as a teaching also. I would have joined a college, and there also I would have contributed sufficiently. But well, my guide thought that I will be more suitable there, and then he advised me that you better join there. And I went there, and I stayed there for 38 years, and after that another 11 years I worked as a professor, and I'm still an adjunct professor in that university, because they are not able to get a teacher for space dynamics, because this subject is not so easy to teach. It comes from different areas. For engineering student to teach, you have to refer quite a number of books, and from each book you get one chapter from here, one from here, like that. Because of my vast experience of this 3 years research in Delhi University and 38 years there, I could manage and then make out as a good course, and the course is still continuing there, and still I have taken classes for them. So I'll start with this. See, this country, we started with a very humble beginning. It was not a government department like this ISRO now. It was one autonomous body, and this TELS was selected. Why it was selected was, it was very near to, this TELS is Tumba is a small village near Thiruvananthapuram it is called now, and it is very near to magnetic equator, and magnetic equator is very important. You will see, next slide please. You can see this side, Earth magnetic field deflects most of the solar wind, whose charged particles would otherwise strip away from the ozone layer that protects Earth from harmful ultraviolet radiation. So magnetic field, if it is not there, our life is in danger. So this is what it helps us, because without this ozone layer, our survival will become difficult. So many people will get cancer and other problems. So magnetic field, because it was near to this Tumba was near to the magnetic field, and also and they could identify it, because actually it is a Cologne is little bit away up if you see in the map, there it passes, but then there was no place there where we could our people could put up a station. So they found out here there was a hill there, some sea area, some area they located, and then they got one church. One church was given by the for this purpose. So originally there was no money, so the whole research started in a church. Next slide, please. You can see here this is geomagnetic equator. So this geomagnetic equator plays a very important role. So here a launching station was established internationally, and people from different countries were coming, and they were doing their experiments over there. Next. This is you can see the church. The church now, at that time, even Dr. Kalam and other senior people used to sit in these offices. They used to have office here. Launching pad was near to the church, but now today this is one of the best museum anywhere in the world, because now ISRO had money, everything is there, and these are all full scale models for our rockets. Next slide, please. You can see here again a view from the Space Museum, and these are all kept there, and this is open to public. Even then, the Vikram Sarabhai Space Center is a secured area. People cannot go just like that, but this museum area they can go. They can have a pass there, and people issue there, and they can see this museum. Next slide, please. These are all the thing. You can see some of the senior scientists how they are doing. They are carrying this rocket to the launch pad at Tumba. Next slide, please. Again, these are views from there. The church is there, and the view from the sea, because the sea is there. Next. One of the senior scientists carrying, because there is no money, on cycle the payload. This is upper pass, whatever instrument they are doing. So over that they are carrying, they are taking it to the launch pad. Next slide. You see here, can anybody find out where is Dr. Kalam in this? Which one? This right one. Anybody else? Any guess? Yeah, I think, am I coming on the way to some of you? Shall I locate some other place? I'll be somewhere here. See, Dr. Kalam is from other side second with the tie. That others are all with tie. The first one, these 5 people actually were responsible for lot of development initially. All were selected by Dr. Vikram Sarabhai. Dr. Kalam has not gone abroad to get any doctorate. He did his BSc Physics, and then he did his MIT from Chennai, and then he was looking for a job. He worked for some time in defense, and then he was selected for the position of engineer at Vikram Sarabhai. It was not in the beginning called Vikram Sarabhai Space Center. It was called SSTC, Space Science and Technology Center. And then this is Kalam. But these 5 people And from this side, right side, the second, Dr. Y.J. Rao, he came from US, and he developed the entire Sriharikota, where we all launching take place. All our rockets, they launched. It was a huge island, 4,000, 40,000 acre. You can imagine 40,000 acre. A large part of Delhi, some part of Delhi will be consumed in that 40,000 acre. One part of this thing. 40,000 acre is a big number. So Sriharikota is that much. So, but because we need them, because where launching takes place, nobody can be nearby. Otherwise, they will lose their ears. So these are this very classical photo. Next, now satellite launch. You can see here the top figure, Dr. Sarabhai, middle, and you can see here Shrimati Indira Gandhi and Kalam is there. Dr. Kalam is there. Professor Dhawan is there. Professor Dhawan is there. These three, and this is the picture of the Dr. Kalam. The first law, when I joined in 73 there, this was the only project, major project in Vikram Sarabhai space, because Sarabhai unfortunately died very early in Trivandrum, came on tour from, because his place was Ahmedabad, and he was also the director of PRL also. So he came at night, he died got a heart attack, and morning he didn't get up. So otherwise India would have still, in my opinion, we would have progressed still faster. So this SLV3 was, he chose Dr. Kalam as the director for this. This was all everything. See, in this technology, especially rocket technology, nobody gives anything. You have to do everything at home. Even small things also people will deny. And we were, today's date, our situation internationally is one of very strong. But in between we suffered quite a lot. Even some of the screws were required for some certain things. Even those were not given by outsiders. So they denied us a lot of things. But our people, because it doesn't come space technology by one person. All kind of people work. Physicists, mathematician, chemistry people, all other areas, engineering, electronics, communication, computer science, mechanical, civil, means everybody, all kind of engineering and basic sciences are involved over there. And then only things, instrumentation. So everything, then today we are in a very strong position. In fact, today news I was so surprised that NASA wants our technology, that Chandrayaan 3, when we have put it, that the technology which we have used, they said, why don't you share that technology with us? This is a great, you can say, achievement of our people, our engineers and our people, that NASA is asking us to give our technology. And this is not a confidential open, it has come in, our chairman has given, Somnath has given a statement yesterday, and today I saw that. So see, you can see where we have reached, because ISRO has a very openly, they take advice from wherever it is available in the country, IITs or universities, and they give projects also. In fact, when I was a professor in Karunya Institute, Karunya University, I completed 2 projects, one for ISRO, and that L1 what has gone, I did a 1-year project for that. At that time, because this Aditya was started long back, but it takes time, to mature. It takes a lot of time. So they don't. They give response projects, and many projects in there by our colleagues in Delhi University also they have done for ISRO. I did also one. I was also very happy then when this Aditya was. They said it will be launched, because we did the background study, and we gave them everything. They said you have to give us the programs, whatever you have developed, and they said a particular language also, because probably C++ or some language. So they said you write all the codes there, and so I'll tell you, mathematicians play a role many places. Maybe directly they may not become all the time project directors or anything. They may, but behind the scene they play a very important role in the development phase and in the many areas they play. So this was a small, uh, uh, from today's point of view, it was small, but that time it was big to us because you can see weight was only 17 ton. When I will tell you later, height was 22 meters, and it could do only 40 kg satellite, and it is a 4 stage. You come next. Yeah, these are all it had a, I will tell you when it comes there. See, the first mission failed. Why it failed? You can see there. Faulty valve caused vehicle to crash. 317 seconds after I was there in Sriharikota because I was specialist in launched orbital lifetime calculation. How much time it will remain in orbit? That was the task at that time I was doing. So it failure was mechanical, but rocket technology is so difficult that one failure, the entire mission. It may be 100 crore, it may be 50 crore, it may be 200 crore. Everything goes. We can't even tolerate one failure. That is the problem with rocket technology. So this failed. But then at that time, Dr. Dhawan was the chairman. We were in Vikram Sarabhai, we all were gathered. And then he says, Kalam, you come. It is not your failure, it is my failure. See, leaders, are very, that is how the leadership works there. As chairman, he said, my failure, not your failure. You did your job correctly. Somewhere I have faltered. So because there are, so many people work. See, one ball opened but did not close. So that because they're jamming, so it jammed, it did not open. So what has happened is they were trying to control it. When it jammed, so vehicle took a loop. Because if it has opened, it will come again in straight. But did not come and then it took loop. We saw that loops going over there. So that's but then you can see the next one. No, please be there. The second flight weight was 35 kilogram, and actually original aim was only 400 by 400. 400 means the perigee height means the distance from the surface of the earth was 400 kilometer, and because if it is a circular orbit 400, but if it is an elliptic orbit, your near distance and far distance will be different. So there our plan was 400, but they were all solid technology. Solid booster is like Deepavali. So once you fire, whatever energy that rocket has got, it will burn fully. So solid we can't control. So it has overestimate life. Its energy was more, and so it entered into 312 by 908 kilometer. That means our near distance is 312, but far distance by 908, and it remained for 373 days in orbit. But our aim was that if it crosses 100 days, our success is 100%, 100 days or above. So it was a 100% success. Afterwards, it was reorganized because success is there. These were not our goal. These were our intermediate goals. That okay, we can't go in one step to our PSLV. Finally, PSLV was the aim of the country because that was the one from where we can achieve lot of useful things for our people in the country. So for that, but then these were required. And as I told you, we had only solid propellants that time. For liquid propellant, what we did is our people sent one team to France. A large number of people of they went to France. In return, we gave to France some components built in India like that. So our engineers, 5 or 6 years they were there. They learned all the technology, and then they built that liquid engine in India, because and it has done wonders. PSLV is one of the best vehicle anybody has in the world of that class. Failure rate was almost zero later on due to, see, reliability plays a very important role. If your quality reliability has got, if your quality you don't maintain, you do a small error, that is sufficient to kill your mission. So, but it was going continuously as a success. In fact, I tell you that PSLV did so good that people even from Russia, once I was there in 2005 in a conference, private Russian people were planning to send human being through that vehicle around in human mission. He said, your vehicle is so accurate, it doesn't fail, and where you want it goes. So we want to send it there. So that was the thing. And then anyway, gradually this other things did, and this mission was anyway abandoned. Next. Okay, these are some of the old picture. You can see Professor Dhawan there, because Professor Dhawan. Another thing was Professor Dhawan said when Dr. Vikram Sarabhai died, then Mrs. Gandhi was the Prime Minister. People told her that Professor Dhawan is one who can. Dhawan told, I cannot take full-time responsibility, because he was the director of Indian Institute of Science. He said, I want to leave directorship of that, because that's a very prestigious thing. But I can be chairman. I will take only 1 rupee from the ISRO, and I can remain chairman. But my headquarters should not be in Delhi, should be in Bangalore. So still our headquarters is in Bangalore only, after Dhawan changed. And Dhawan remained for a long time. He remained chairman, nearly 10 years. And then these are all, the Kalam is there, and his deputy Srinivasan. He also became again a director for Vikram Sarabhai Space Center. So these are some of the, here you can see Sarabhai and Kalam talking. Next, and there is Madhavan Nair there. So these are again some of the past figures. Next. So these are the launch vehicle, how we started with a small SLV, then ASLV, then PSLV, then GSLV, Mark 1, Mark 3. Mark 1, Mark 2 difference is, Mark 1 Russians gave us some engines. See the problem I tell you, Russians actually had problems, they had financial problems, serious problems. So they wanted to sell their energy, their entire technology to India. But then Americans said you can't sell, because Americans were the dominators in the world. They are the leaders. So they said you can't tell, you can only give them some engines. So they gave us only 7 engines. So that is that Mark 1. After that 3 or 4 we used. But they were, and it was done in such a fashion that you can't do anything with the engine. They will come, they will only do all the operations. So it was not a very useful thing. But in the meanwhile, our people worked very hard. They developed the cryogenic engine, because we did not have the cryogenic engine at that time. So then when we developed our people, then that name Mark II they put. Then in the parallelly our people were working on double the engine. So they made this vehicle. So this is a vehicle, because now we are hearing that human mission will also be there. Some human being will be also sent in the orbit. So that will be done by this vehicle, GSLV Mark III, because it can take, somewhere I have written there, it will be able to take around 10,000 kilogram in near circular orbit. In 10,000 they will manage a space station, and they will take a person, take him around for a few days, and then come back. Next. This is anyway similar to that. Next. This is the Vikram Sarabhai Space Center, where I worked for 38 years. This is the main office of director, where you're seeing the rooms, and this is the bust of the Dr. Sarabhai. Once I saw Kalam came there, and then he said, you take my photo. He said, he stood there, because Sarabhai is the person who has started, he is the father of the space research in India. Space research has been carried out by Dr. Sarabhai. His plans are still, his dreams are still being achieved. So this is the main branch. Other side there is a multi-story building, where I have been sitting here also for a couple of years, but their major life in the multi-story building aspect. Next. So this is again, I think, the repetition. You can go back. This is, I think I have already told you. Next. Okay, next. ASLV. See, ASLV was a wrong step which our department took, but we learnt a very good lesson. What we learnt is that you cannot go for a rocket launch without testing it completely. See, how we do testing is, there are 2 methods. One is mathematically, by computational fluid dynamics, CFD. That time computers were not very powerful, but today we are having very powerful computer workstations, so many, and this thing. So we can do, but that time wind tunnels were there. So you make a small model of this, and then you test it and get results. But unfortunately, there was no time, and our chairman Dhawan has committed to Germans that they will do it quickly. This thing, because he was also a great aerodynamist. But what happened is, sometimes your theoretical knowledge and practical knowledge, there may not be same. There may be different. So we paid heavy penalty for this. 2 launch vehicle failed. Next. 2 launch vehicle failed. But then there was a national, team from various, all learned law professors, everybody, they found out, and then they said, where are the mistakes? What happened is, in the first 2 vehicle is broken into pieces. See the upper in the atmosphere, when it goes, so much load is coming on the vehicle is breaking into the pieces. So that means the length by diameter was not correct. Many things, because it was not fully tested. So this after 2 successes, this project was abandoned, because this was also not useful for us. 150 kg of satellites are not useful. Next. Then from India's first satellite Aryabhatta, which was launched not by Russians, to this EOS in 22, the Indian Space Research Organization has launched a total of 129 satellites of Indian origin and 342 foreign satellites belonging to 36 countries since 19. This is the data till 22. So now some more have been added to that. So you can imagine, we are earning this. Our department is earning the money also. Lot of money comes, because even PSLV, when the data is sold and whenever any launch is there, but our rates are cheapest in the world, because only few countries have this rocket technology. Rocket technology is not so easy. Some people tried, even UK, etc. They tried and they said, thank you very much. They abandoned their thing. Next. So this is the place where Sriharikota is there. Satish, now its name is Satish Dhawan. After the death of Satish Dhawan, this center is called Satish Dhawan Space Center. So that place is there. It is on the eastern side, because we get advantage where Earth is moving, west to east side. So when we launch, so we get the rotation advantage in rocket launching. The rotation of the Earth, that component also adds. We can't have a rocket launching station on the west side. So that's why the Sriharikota was chosen. And luckily we got such a big island. So so all our future needs are also met from that. Next. This is, you can see on that Sriharikota, these are our launch. And there are a couple of, at least 2 or 3 they have made the launching places where they even launch. Next. This is again, now the rocket is ready for launch. Next. This is PSLV launch. PSLV had till that 22, 54 launches. So out of 54, 52 were successes. The first launch of PSLV failed because of a software error. It was not the hardware error. Otherwise, PSLV would have a very, very unique record. That it would have been, the error was very, very small, but the entire thing failed. Somebody who wrote the code somewhere left one place and it did not fill. Plus or minus something should have been written. So it has taken one sign, and that sign has gone into the opposite side and failed. The mission got failed. Again, it had the same problem. Otherwise, this mission would have also been successful. All PSLV would have been successful. Next. PSLV polar, this has got a very unique first stage is a solid, second is liquid, third is solid, and fourth is again liquid. And this is a very unique, only we are doing. Others, nobody else in the world tried this combination. But it has been extremely successful. And these are all done by our engineers. Nobody is there, not that people, all young people like you, after some time they join and then they debate and they find out. And this has been an extremely excellent vehicle, which it has earned a lot of money for our department also. Next. You can see there what I told. It is written there: first stage, and second stage, third stage, fourth stage. Next. PSLV 37 successfully. This was again a record that time. That 104 satellites in a single flight. See, major problem is when you launch 104 or a large number, their separation is done by a mathematician. He was working in my division when I was there. and they have to do all lot of mathematical calculations that they don't hit each other. When they are separated, again it is done by a mathematics person, and he does. He is the head now for the division, applied mathematics division. He is the head now. So they do 104 was a difficult thing, but he did it, and everything was successful. Next, this is the flight. Next, this is the how we, if you have 2 points in space, so and you can find an orbit uniquely, but then any small change you make, the orbit will again, everything will change, x y z, x dot y dot z dot. But if you define them in another coordinate system in terms of orbital elements, then you have only one parameter will be changing, others will be constant. So that is what it shows. So you can see there gamma. When sun comes on Earth equator, it comes on 2 times, one from south to north, another from north to south. When it comes from south to north, it comes on 21st of March, and if you join center of the Earth to that point, so that will become your x-axis, and then you take z-axis from Earth equator. When you draw a perpendicular, that will be your z-axis, and you form a right-handed system. So you have a coordinate system. Otherwise, and this is the inertial coordinate system. See, if we are moving, sun is moving, everything is moving in the space. But if we don't have an inertial system, we cannot say today. Now on your thing you can find out where which plane is where and what location, and even when you go, you are able to identify the places and everything, or your Google map is working. And so this is all because you have an inertial system, and this is defined like this. This is the coordinate system. There may be a small correction you have to make with respect to time, but that correction is, we know how to make correct. But basic definition comes like that. X-axis, wherever sun comes over the Earth equator, join that, and this gamma, this is called vernal equinox, and then z-axis and y-axis. And this capital omega, this angle is in the xy plane, and small omega is in the orbital plane. This is the orbit of the satellite, and theta is called true anomaly. True anomaly is measured from the, if you have an ellipse, you have two focus. So from one of the focus, when you measure that angle on the xy plane, on the xy axis, you can say, or the major axis, that theta is the true anomaly, and r is the radial distance, and v is the velocity. If you have r and v, you can, that means r has got 3 components, v has got 3 components. So with that you can find the orbit, but that orbit can be converted in terms of these parameters: capital omega, small omega, theta, and angular momentum. Angular momentum you can define. These are all mathematical. Mathematics people understand faster than others, because I am telling next thing, I am going to define a very important thing. So this capital omega, you remember, this is the angle here in the xy plane, and small omega is in the orbital plane. These two angles you remember. Now what happens is, next slide please. Now sun synchronous orbits. See, the entire thing which PSLV was there for sun synchronous orbits. Now the definition you see: orbit with the secular rate of the right ascension of ascending node, capital omega, equal to the right ascension of ascending right ascension rate of the mean sun. Now sun, how much time it takes to how much time Earth takes to take one round around sun? 365 days, correct? 365.25 days, correct? Now, so these are relative things. So sun around Earth, you see, now you take it other way around, because all are going in space. Now in 1 day, how much sun will be moving? 360 degrees divided by 365.25, correct? That is the number, that 0.9856 degrees. Now that number must be equated to d omega by dt. Omega, I have told you, angle in the xy plane. Now xy plane, now this is the, supposing this is your orbit. This is your orbit. Now this orbit can move this way because of Earth. You know Earth is not sphere, correct? Earth is oblate. You know difference between polar radius and equatorial radius. How much? Anybody? Approximately 10 kilometer, 20 kilometer, 30 kilometer. How much? It is between 10 and 30 kilometer. It is around 22 kilometer. Okay, that is the difference. But this difference in Jupiter case, equatorial radius and polar radius, difference is 6,000 kilometer. For Jupiter, the difference between equatorial radius and polar radius is 6,000 kilometer. For Earth, it is only 21.6 kilometer. Because of this Earth, if Earth was sphere, then whatever I am writing, it would not have given any meaning. Because Earth is oblate, so this has come d omega by dt. The three things happen. Three things happen. This plane moves like this. This plane moves like this also. And the satellite moves little bit faster. Little bit faster. So mean motion increases and period decreases. Period is defined by 2 pi by mean motion n. So period of the satellite decreases because of oblateness. This oblateness was the only thing which I put in my doctoral thesis in three body problem. So I had fair good idea about the oblateness. So this we teach to our students in space dynamics, and this is because sun synchronous orbit is very important, because we spent all our energies to get sun synchronous orbits. So sun synchronous orbits are like repeating also. See, supposing you want to find the situation around this area, so that satellite will take a photo, but it may not take full photo. But then next day, if satellite comes in the similar environment, then it takes, then those can be patched up, and you can make an entire thing. You can make it. So this is why these sun synchronous orbits are very important. So major task which Dr. Sarabhai at that time told that our PSLV do sun synchronous orbits. So definition comes from mathematics. So that J2 is the coefficient coming because of Earth's oblateness. That number is also given, J2 number. Here I have not mentioned here, but somewhere it will be there. So that J2 and N is there, and Kepler's, you know Kepler 3 laws. Anybody knows? Can somebody tell? Kepler 3 laws. You have studied, in 11th, 12th. First law says, okay, I will repeat quickly. First law says that every moves in an ellipse with one of the focus sun. Second says area in equal time. Yeah, equal area in equal time. And third, T square is proportional to A cube. These are the three. So that your third one comes, mean motion comes from the third Kepler law. N is equal to mu by, because mu is the gravitational constant of the Earth. Okay. If you are finding Earth satellite, if you are finding Moon satellite, mu can be, for Earth satellite, mu is, for Earth, this is 398600 kilometer cube by second square. That is the unit. But for Moon, it is only 4906 kilometer cube by second square, that number. So from there we get N. So when you get N, J2 value is known. I have not written, but that J2 value is 0.00189 of that order. So, and then P is nothing, the semi-latus rectum. You study in ellipse all these things. That's why mathematics people learn this faster, because they know all these terms. And that rise ascension of mean sun, that number I already told, 360 by 365.25. So with this, now you can find out the angle. If I give you any orbit, and you can calculate everything, so you can tell me from this equation what is the angle, so that this becomes a sun synchronous orbit. Understood? Because I is only unknown. Other things are all known, both sides. So with that is how you can define a sun synchronous orbit, either elliptical or circular. Both you can define. Because you are all mathematics students, so it is easy for you to understand. That is the thing. Next. So this PSLV was a great vehicle, has been, when we were doing it, I was only over there. So it is 44 meter tall, 2.8 meter diameter, and you see weight from that 17 or 39 ASLV. ASLV we never thought it was we should have gone, but from the initial 17 we went to 294 tons, 4 stages. I already told you the stages: so solid, liquid, solid, liquid. And in low Earth orbit, LEO means low Earth orbit. It can put satellites of the order of 3,250 kg, and sun synchronous orbits. See, sun synchronous orbits. Another thing, please go back. Yeah. Now this side minus is there. Left hand side. Either this side is plus. Now what will be angle here? Whether angle will be in below 90 or above 90? 190, because cos is negative in the second quadrant. That is important. So mathematics people only understand faster, because sometimes engineering students forget their quadrants also. Which quadrant, what is positive, what is negative, they forget. Because I taught 11-year aerospace engineering fellows, and they have a problem. You ask, suddenly you ask them, okay, cos is negative in third quadrant or positive. They are not very clear. So angle will be more than 90. That one thing is proved here. All sun synchronous orbits are inclination is more than 90. This equation tells, isn't it? This equation tells. Next. So that's why the weight is less. Sun synchronous means you are going like this. You have to make angle. So you have to do. See, this rocket can be. This is pitching up down. This is yawing. This rocket is going like this. This is pitching, and this is yawing like this, and this is rotating. So it has to do yawing, get into 98, and when it goes to 98, it loses the energy, and that's why we are getting only 1600. And GTO means the height is the 36,000 kilometers. So you are taking 30, but you are not wasting in terms of rotation. Whatever angle you have launched your rocket, same angle you can achieve in that. Only thing is later on you have to change the angle to 0. So some energy you have to lose there. Next. These are all photos, because we are not able to see, but if you see on this small thing, you will see nicely Himalayas seen by the photographs from those satellites. Next, you show them quickly. Jaipur, and this is the one. This is Lonar Lake was created by a meteorite collision impact. It is one of the 4 known hypervelocity impact craters in Baltic rock anywhere on Earth. You can see the size. Lonar Lake has a mean distance of diameter of 1.2 kilometer, and that is object coming from space and hitting Earth, and about 136.7 meter below the crater rim. The meteorite crater rim is about 1.8. So this is there in our country. People go there to visit. Next. This is Vijayawada. Next. This is on. If you see on a computer, you see them nicely, but because it goes, we don't see that much. First day image of Cartosat 2 series. This is Cartosat 2 series. Okay, next Bombay. Next, Cartosat satellite helped. See, when that our army, our fellows did that surgical strike, Army, Air Force, etc., Air Force fellows. So all this information was available to them, because they are very accurate. So they knew which are the places those fellows are there. So they have planned everything, and they had the surgical near-made surgical strike. So they knew where to hit. So they hit those places. These are very accurate ones. I have seen the images in Bangalore, their strike center. They say the accuracies are at that time, long time back I have seen. They say less than 1 meter or less than half meter accuracies were there. You can see there. You can identify. Next, now our standard must have gone further better. So multispectral imaging of Midoriya, UP, taken on this date. Next, Doha. Next. Now, Gujarat IT department uses ISRO satellite images to nail tax defaulters. So they will do, the crop 2-3 years, and some people will claim I did this, but they are able to find out what is actual. So they have there in their thing that okay, you have not done anything, and but you are claiming. So that they are using this thing for that purpose. Next. So this was one important thing which we did, and I was also actively involved in the space debris thing. And only one mission we did, so we brought it back. Now it will be required for our human mission, because a human being have to be brought back. So this is the one very important day, important mission which we carried out. 12 days it was in orbit and re-entered Earth atmosphere and splashed down into Bay of Bengal with 12 meter per second on January 22, 2007. Next. Its flight is given there, how it has come there. Okay, next. See, these are all, when any debris comes, when two bodies hit, lot of debris will be generated. And those debris, with the time, these, I told you that capital omega change. Similarly, small omega change. There also, the oblateness will change 3 parameters. Mean motion, small omega, d omega by dt, and d capital omega by dt. Because of that, if any collision takes place, after time, once something hit, a new orbit come for everything. So they will change with time, because their rate of change of small omega, capital omega will be different. And that's how you can see this cloud of debris. So this is Chinese. What Chinese did, they killed at 800-kilometer altitude, they killed their own satellite. But they killed at the time when our SRE was there. So we were afraid that our SRE may get killed. Because one of the debris, if it hits our thing, then our whole thing will be, maybe they had that idea, but they can't hit our thing. But they hit there, generated more debris, and thought that some debris, and some debris were coming very nearby, as near as less than 1 kilometer, maybe 500 meter, 400 meter, like that they were coming. But our, and in fact, one night I was doing it, we were doing, our team was doing, I told the mission director that this is there what we want to do. And he says, let us take a chance, we will not, we have the capability to change the orbit slightly. But then he said, no, we will not take chance, let it continue. So luckily it didn't hit. But if something hit, then our SRE mission would have failed. Because even a small thing hit, well, and that is the, in space, that is the problem. Even a small hit. So right now, space debris is the big problem for, like on, you see, when you reach sometime, traffic jam is there. But here only traffic jam is there. But there, once you hit each other, the whole thing will go. Next. नहीं सुनाई दे रहा. So this is the one, you can see that the debris which happened, that what Chinese did, and suddenly the China, that debris have increased, and that was natural. That iridium cosmos, that was a natural hit. Nobody did anything. Only thing, iridium was an active satellite. Iridium people could have managed to do some change in their orbit. We do in ISRO. Our people do it in ISRO. Whenever something is coming nearby, they do small change in the orbit. But iridium people did not do. Iridium was a full system, not one satellite. So many satellites for communication. So if they lose one satellite, then their entire thing has get into problem. But unfortunately, that has happened. It happened, and you can see the debris changing. Suddenly, the increase is there. So that's why I showed this is because we were afraid that our SRE would have got into problem. But then this is the scenario which the world is facing now. Next. This is again the path of that SRE, how it was coming to the For some time, we don't get any signals. That is called the blackout. Blackout period is we all we all at that time uh, uh, just pray that after some time we should be able to get the connection. We should be able to get those signals. So when signal comes, then there will be a big big clapping in our control room. Next, this is the army people, who are bringing it to the seashore. Next, these are, you can see here, they are bringing nicely. Next, and this is Mark II. Mark II GSLV. I told you Mark I and Mark II difference is Mark I was the cryogenic engine was Russian. They gave us only 7 engines. You could use successfully only 3 or 4, I think. But Mark II is ours. That is done by us only. You can tell me when to close so that I will quickly make it. Mark II. Next, these are all the place there, and these are all Sriharikota images. I mean the complex there, how the rockets, etc. Next, this again, the rocket is there ready for launch. Next, and it stands of its own. The CGs are so well built that there is nothing holds it later. It stands of its own in the end. And these are all again the rocket launch. Next, now GSLV Mark II is a 49-meter tall with weight of 414 tons. It is 3-stage. It has got now 1 stage got reduced. So first stage comprise a core motor with 38 tons of solid propellant and 4 strap-ons. 4 liquid nearby, that is strap-ons they put around. So that is each 40 tons of liquid propellant. That is UDMH, UD25 and N2O4. And second stage is again liquid. And third is a cryogenic. So here we have our people only developed this cryogenic engine, 12.5 tons. Here liquid oxygen, see, handling this liquid oxygen, liquid hydrogen is a big task. But anyway, our people have. That's why I said physics people, liquid physics and different kind of people, they work there. Next. This is again one of the profile, how that goes. You can see here, separation takes place after 17 minutes. And then altitude at that time is 213 and velocity achieved is 9.7 kilometers per second. We reach that. See, some people asked that the people, Russians or the other people went to moon very quickly, but we have taken time because they have very powerful rockets. We don't have that kind of rockets, so we have our own way to reach there. That's why we take time and so gradually we increase the orbit. But unfortunately, Russians lost when they were going ahead of us. But if they would have gone in few days. But then they hit somewhere, some mountain they hit, and the thing was over. Next. Again, this GSAT 14 was because when our Mark II, when our cryogenic engine was made indigenous, so we all were excited that how it will work. But it did a very good job. Next. So these are all different spacecrafts, communication satellites, Earth observation satellites, scientific satellites, navigation satellites, experimental satellites. So these are all different classes of satellites. Next. This is why I am showing this is same launch if it does a different time in a day. Say you have put same launch, only time you have changed in a day. How much life of the satellite can change? It can be from few months and to millions of years because of the location of the sun. To develop this particular graph, we have developed, me and my team developed. We took 6 months time on computer and supercomputers we were using to develop this particular figure. Why we show this is that the location of sun plays very important role on a high altitude satellite. Sometimes it brings down, sometimes it takes up. So in one of the case, I saw that 173 perigee, lowest distance, was raised to 1000. 173, there is lot of drag, atmospheric drag, but at 1000 drag is almost negligible. So we knew that it will never come back, never come back. It will be millions of years of life. So this is what this slide we show to tell people. Well, originally the perigee was 181 to 32,000. This was our first launch from our indigenous one, and we were doing the our cryogenic stage will come back, because that becomes a debris. So we wanted to know, but that incidentally came quickly. But if it was done different time in a day, what will be this scenario? So this has been is one of the very rare picture in the literature. Many people have cited this. Next. Now you see 1 minute difference. If 1 minute later you launch, so you can see the perigee apogee difference. In one case it is coming down, another case it is not going. It's going up. You can imagine. Launch date at 3 minutes and launch date at 4 minutes has got this difference. So this is the difference of one minute in sun location. These are all I picked up from a published work to tell that, see how much sun can play a role. Because when we do re-entry studies for the bodies, they are coming back. So we need to take for the orbit which are little bit higher, the location of the sun and the moon also, and the gravitational effect of the sun and moon also on our moon does not do that much problem, but then sun can do. But moon also at times play a very important role as a subsidiary, like a catalyst. Sometimes a catalyst can develop a lot of changes. Next, this is the debris. In 57, one satellite was launched, and then gradually you see next. You see, after 56 years, the like Delhi say, when I was studying in Delhi University, 65 to 70, there not many, the crowding was there. I used to come from Teen Murti to area to this Delhi University, Amjas College faculty. But we didn't see much problem. But today you see how much is the difficulty. You must be feeling those who are coming from faraway place to this place. Similarly, there also the problems are coming. Next. So space junk, a lot of junk is there in the space. So these I have just put it. This can be, my lecture can be shared to all those who are interested. They can have a look. And so a lot of debris have come now there. And the U.S. Air Force Department, they do the orbit determination every day for some of the bodies, in the sense that all bodies in near Earth environment whose diameter is more than 10 centimeter or 36,000 with 1 meter. So they are available, and they are available in open space, in the sense that one site is there where you have to only take from them www.spacetrack.org, space_track.org. Only thing they will ask you for what purpose you need, etc. They will give you a password, and later you can download all the details about this. But it is not, it doesn't cost. So there are a lot of data about these satellites are available. Next. So this is are the countries, with the most satellites in space. So our name is also there, 58, and Japan and others. Maximum are for USA. So this is then China, then the Russia, and like that. Next. This is again in distribution of satellites in orbits. So low Earth, LEO means low Earth orbit. Mostly they are there, and then MEO means middle Earth orbit, medium Earth orbit, and GEO means 36,000 kilometers. So they are useful. Wherever useful, the only people will send there. Now you see last line, collision with 100-gram debris flying at 10 kilometers per second. Speed is like a collision with 1000 kg car at 200 kilometers. Normally 200 kilometer on our roads, only maybe on our highways or somewhere it may be there. So that is the same effect. So space, now you can imagine what damage they do. What damage they can do, 100-gram debris. So this is just to give a example. This is the damage in space. It happens if it hits. Our space station is there. They have done many times to avoid this debris. If they find that debris might hit or coming nearby, they do little bit change in their orbit so that it doesn't hit there. Next. This is their space station. So they have done a number of times this orbit changing. Next. So these are all because this is, as I told you, after our engineers came from France, they developed that Vikas, and that has handled all PSLV. And now this is India's cusp, that is cryogenic engine. Our engineers have made this also. So we are self-sufficient now. We don't have to take from other people this technology. Next. And this is a satellite. You see the complexity of a satellite, GSAT-14. The complexity of the satellite, you can see here how much. This is all done in Bangalore. Now it is called U.R. Rao Satellite Center. After the death of U.R. Rao, who was the chairman of ISRO, after that, when he died, and then this center has been renamed as U.R. Rao Space Center. Next. Now when we go, to moon or somewhere, we don't go in one this thing. So we achieve it gradually. As I told you, one thing is we get a better idea. Another thing is we don't have that powerful rockets that we can go that orbit in one round. So we go, and then every time at perigee we will add some energy. Of course, we have to carry that also in our launch, but that carrying is easier than having a powerful rocket. Somebody may say, finally you are reaching, but we are not reaching in one go. So we are same thing, whatever we did in Chandrayaan 3, 2 or anywhere, so we do like this only, or even L1 now, L1 mission, Aditya mission also we do the same thing. So we do like this gradually. And what we do, see, another great thing which our country has done is we have very large antennas now. Even the L1 point, that is 1.5 million away from Earth, between Earth and Sun. We will ourselves track, because I asked my friend who was working with me, now is the director. He says, no, we are doing ourselves. I thought maybe we are taking from JPL or somewhere help. No, we are doing ourselves. So that is a very great achievement which our country has made. And they are doing space debris monitoring also, but not all, to some extent we are doing. Next. This is Chandrayaan 1, like that we go and then go to the nearest. See, if they go nearby, and when they go nearby, if they don't capture it, for capturing what they do is, they put retriever rockets and put it into a orbit, elliptical orbit. If they don't put it, there are two things can happen. If there is wrong calculation, it may hit, or it will go in a hyperbolic orbit. So they capture it and put it into a elliptical orbit, and that then gradually they make it circular. Or in the case of Chandrayaan 3, they made it around 169 kilometer altitude. From there, whatever that lander and other things, from there they gradually bring it to the moon. And now our technology of that, last time we failed because we had wrong strategy in the bringing it down. We put 5 motors, and some problem came there, and we had this thing. But this time 4 motors were there, symmetrical. And because one of my friend professor from IIC Bangalore, he was doing this. So recently I met him. He told that this, and his strategy, he is an expert in control guidance, other areas. So he says this time the strategies, even before launching, he said this time it will succeed. So that is the confidence our people had before the launch, because they did lot of experiment in Chandrayaan 3. Because whatever we lost, we failed only for landing. Other things, that orbiter was still there. because from that orbiter we get lot of advantage. See friends, another problem in moon is because since moon the it takes around 29 days. Moon takes around to take around Earth one round. About its axis also it takes same time. So we see only one side. Whatever moon you see, only this we see. Other side we never see. Because as you see, I am here and I am going, but I am going at the same time like this also. So what has happened is only front side only you see, back side you never see. But our people planned to launch it on the southern near to South Pole, other side, and they did it successfully. So India has done a good job. Next. Again, you see, when you go near to that, again we capture it there and put it into elliptical orbit, and then we gradually bring it to a circular orbit of our use. Mostly lunar orbits are 100 by 100, but it is not a hard and fast rule. You can have anything more also. So this mission we had a slightly more, and first time we had 100 Chandrayaan 1, Chandrayaan 2 also, but from there we can come down. We have the propulsion module, we have the lander, and we have the rover, all those three. And this time everything was perfect. Only thing is they were trying whether after 14 days, because 14 days means since because of this rotation, we take same time 20. So 14 days night, 14 days day. So in night the temperature goes to minus 200 degrees Celsius. Now they close everything. They might have done experiment on Earth. Earth it might have worked also, but Moon maybe because of those severe conditions, they might have generated those conditions in a lab here, but they were very hopeful that it may again after 14 days may work when sun again it comes day there, but didn't work. Some problem may be there because of the temperature. Because for 14 days it is lying in minus 200 degrees Celsius. When again day came, they could not do it. Next. Yeah, this is all the profile. Same thing again I am showing. Next. Chandrayaan 3, Chandrayaan 1. Yeah, Chandrayaan 1 only I told you already. Next. This is in first Chandrayaan we had done one MIP. We took something and we hit it. That was again the idea of Dr. Kalam. He said, why don't you? At that time we did not have any plan to put it. We were not prepared for all technologies we didn't have. So this was done and this was successful. We hit it. Next. Next. These are all pictures taken from that Chandrayaan 1. Next. Chandrayaan 1, 3D view of moon. Next. 3D view of moon again. This is a crater, lunar south pole. Next. Chandrayaan 2. Okay, next. So again the technology is same as I told you, you go and then you go there and then you bring it and then you take from there you go. Chandrayaan 3 also you can see here. Chandrayaan 3, the mission life is one lunar day. Mass was 1749 kg, including rover, lander module and rover module you can see there. And this is why it was done by the Mark III. That is the one which I showed in the end, where we have used the powerful that our cryogenic engine, 25 ton. So that vehicle was used. It is 3 stage. You can see there, and that was it used because that only can take this much load, and and then it has come into that orbit, and gradually it was made that the orbit 100 kilometers it is showing there. And that's all. And then later on, it has gone. And the major thing happened from the predicted one to the actual where it landed. The difference was not much. So you can see the kind of landing and execution was so accurate that because the confidence which the engineers had in Chandrayaan 3 was excellent. But only thing is they were still They were trying to see whether it will work after 14 days. That in this mission has not worked. Maybe in future they may have some other thing, technology that may work, because one for 14 days when it is lying in minus 200 degrees Celsius, they might have closed them nicely, but still, even if there is a small, because they are done only by from the signals there, still there may be some lacuna may be left, and even if a small thing enters, small cold enters there, the entire thing will become cold inside, and the instrument will not work. Next. So Mars mission we did. India was the only country who have done this first time success. And that time, whatever energy we had, we utilized fully, optimally. And these comes, opportunities are not there every day. I have shown here. That is again mathematics. Mars. So we first and second stages of PSLV C25. The next. Next. Okay, this is again the profile for that. The entire thing, how various thing happens, all stages, separation and ejection, etc. So it takes that much time, 44 minutes, etc. And this is the velocity you need at that time. Next. So you see, this comes again from mathematics, Hohmann transfer. When you go from one planet to another planet, you join by a elliptical orbit. And when you can see over here, both the cases are there. Supposing Mars is outside us, Venus is inside. So both of these can be done from here, Hohmann transfer. Next. Now this is the period by which we know what is the time after one launch to a next we can have. Synodic period. Synodic period is again, you can calculate 2 pi n2 minus n1. And when you convert them n1, n2 in time, so T synodic is T1, T2 divided by T1 minus T2 mod. And for Earth and Mars, let us see. Earth period you put in terms of days. When you calculate 777.9 days. So that is the next opportunity. After one opportunity to this opportunity, this is the average time which is needed. You can't have as and when you want the launch. That's why when a launch was opportunity was there. So whatever we had propulsion available that time, so we utilized, and we could manage only a highly elliptic orbit. If more energy was available to us that time, now we have more energy because we have Mark 3 also. So we can put even maybe we may be able to even put a satellite in over Mars also. Just like here we are done on Chandrayaan. A re-entry also we can do. Next. So these are the opportunities on 299, 275, 239. Because a different scenario, the locations will be different because they are in elliptic orbits. Next. And this is the period, again they come from Kepler third law. So the time period, going from there to Mars is 258. So people say people can go to Mars and come back. So you need double of this time, minimum. But these are ideal. So you add some more. So I have been hearing that people are going to Mars. Not we, but our country, but other people. But so far, no manned mission has gone to Mars. Only planning is going on, but it's a difficult also. 500 days, more than 500 days, people have to be there. Next. This is against that's next. Interplanetary transfer. 3 phases takes place. One is you are around the Earth. Then you go in between phases. Heliocentric means sun. Helio means sun. Sun as the center. And the third one is planet. Suppose you are going from here to the Mars. So these 3 phases you go. That's how this. And there is a term like sphere of influence. Again, mathematically you calculate. Mass of the planet divided by mass of the sun. Raised to about 2 by 5. And then the distance between the planet and the sun. That will be the For Earth, this is 9 lakh and 60,000 kilometers. For Moon, it is only 64 or 65,000 kilometers. So Moon sphere of influence is within Earth's sphere of influence. Next. So that is how you go 1 second and then you go around that. Next. This is again a very famous theorem, Low-Lambert theorem. If you are having two departure and arrival, and if you know the time, you can have only one orbit. You can't have no more than one orbit. It's a very famous mathematical theorem, Lambert theorem. We teach to students, and entire proof is by trigonometry. All sin A plus sin B, cos A, cos B, all those formulas they come, and from there you can prove this Lambert theorem. Very interesting. Next. Yeah, this is Mars going, and you go initially when from Earth it starts. Mars is ahead because Mars moves slowly. So that angle is around 43 degrees. When you from Sun, when you join from Sun to Earth and Sun to Mars, the angle between them is around 43 degrees. Because Sun, when it reaches to that ellipse, when we are putting onto the elliptical path, so it should be there. Mars should be ready there to receive it and then capture it. It will go in hyperbolic orbit, but again by retro rockets you can put it. So that is how we did it. Our orbit was around 384 by 80,000 when we did Mars mission. But then it has given some data related to atmosphere. Their atmosphere is thin in Mars because its gravity is less. It losing some of the atmosphere. Maybe 1,000 years back, atmosphere maybe more, or even 5,000 years back, but gradually it is losing. So going to Mars means atmosphere less there, only carbon dioxide is there. But that can be managed, people can take out oxygen and survive there. But then Moon, there is no atmosphere. So Moon going and surviving there is a problem, because it's not easy to be there on Moon. And Mars and Venus, atmosphere is very thick. The Venus, what happened is, at the surface of the Venus, the atmospheric pressure is 95 times that the atmospheric pressure on Earth. So one atmosphere, we are staying in one atmosphere pressure. They are 95, but at 60,000 kilometers, same conditions. So Venus going out of order. Mercury is very hot, no. Only Mars is the one where people can try to go. Moon also they cannot go. Moon, I told you, Moon, the situation is entirely very difficult. Unless you carry everything, and maybe then only possible. Next. So this is how the path, you go and then you take around that. Next. Again the same around Mars, dates etc. I have given there. Next. This is L1, L2, L3. See, when Earth and Moon, they are moving, they move out their center of mass, and so these 5 points, because of their gravity and their movement, rotation, their movement, they get equilibrium there. So any point you put at any of these 5 points, it will remain there. So when Earth is moving around Sun, so L1, L2, L3 also will be moving. So we have gone that Aditya has gone to L1. That is 1.5 million kilometers from us, from Earth. So this is the L1. Here only that Aditya mission has been. Now it will take around 4 months' time to reach there. And there you cannot, again mathematics comes, you can have here L1, L2, L3 are actually unstable. So you can have only conditional periodic orbits. And otherwise you cannot have. But then you can have three-dimensional, planar, you can have only unstable orbits. But in three-dimensional you can have, they are also unstable, but you can have a periodic orbit. And those halo orbits are all three-dimensional periodic orbits. Next. So I have written here, halo orbit is a periodic orbit, three-dimensional orbit near the L1, L2, L3. These are not at L4, L5. L4, L5 are stable, but then reaching there is difficult. Once you reach there, then coming out is difficult. So L1, L2, L3 Lagrangian points, they are unstable, and mathematically we prove, like characteristic equation is there. The roots we find out if two are roots are pure imaginary, two are real. Because of pure imaginary roots, we get the periodicity, because you can write in terms of cos theta, sin theta, and the real roots means that will go on increasing, the part of that, and one of that will be increasing all the time. So you will not get a periodic orbit. And Lyserg's orbits is a quasi-periodic orbit, and that can have, it will not repeat, but it will be like that going on in a different way. But next. So this gentleman actually was the one who made the use of this in his doctoral thesis. He wrote, Robert W. Farquhar first used the name halo in 1966 for orbits around L2, which were made periodic using thrusters. Farquhar advocated using spacecraft in such an orbit beyond the moon, Earth moon, as a communication relay station for an Apollo mission for the far side of the moon. Because L2 is far side, so he said our Apollo mission we can use it. But it was not used that time. A spacecraft in such a orbit would be in continuous flow of both the Earth and the far side of the moon. In the end, no relay satellite was put. So this is how the history starts for the use of this. Before that, nobody knew what to do with them. Next. So in May 2018, Farquhar originated idea was finally realized when China placed the first communication relay satellite QCO into a halo orbit around the Earth Moon L2 point. For Earth Moon also 5 points will be there for any two. Supposing you take Sun, Jupiter, 5, any two bodies moving about their center of mass, whether they move in elliptic orbit, circular orbit, 5 points will be there. So that is how the whole thing started like that. Next. So Aditya L1, India's first sun mission, that is on L1. As I told you, it is on between Sun and Earth, and it is around 1.5 million away from Earth. And it is in a halo orbit, three-dimensional orbit. So large, its period is around 175 days. In 175 days, it will take one orbit. I mean, it is not like a regular orbit like elliptic orbit or circular orbit. It is a thing orbit, but it will close. Orbit means it closes. There, we start from somewhere and it will come back there. So 170 days. We do not know how many orbits it will. Because finally, it is also unstable, so it has to go gradually. But let us see how many days it will remain there. But you have to make some corrections. With corrections only it will put, that will be again challenge. When our people have to insert in halo orbit, it will be challenge. And again, maintaining halo orbit will be challenge. And let us see whether how many revolutions they will be able to do. But each one is 170 days. So even if they do for 10 days, so much it will be done. Next. So Aditya L1 mission is conceived ISRO L1 in a halo orbit as a 400 kg satellite. The satellite placed in the halo orbit around the Lagrangian point L1 of the Sun-Earth system has the major advantage of continuously, advantage is continuously viewing Sun. From there, no shadow will be there. It will be inserted in a halo orbit L1, which is 1.5 million kilometers from Earth. Advantage is because actually we are all, you can say, if Sun is there, we are there. So Sun study, and Sun is the only nearest star. So Sun people want to study as much as possible. So our scientists, those who are related to astrophysics and many areas, there are 7 instruments have been sent in this L1 and developed by different. One is from Vikram Sarabhai Space Center, one is from PRL, one from Bangalore. Like that, different places, one from Pune. Different places people have developed their payloads. So you can see that some new research will be coming, and some more growth to the science of Sun will be available to the researchers who do research on Sun. That will be the major thing. Next. So these are all periodic orbits in Earth Moon. There are a lot of periodic orbits in two systems, which we carried out a lot of research in this. Very interesting way. These are also mathematics full, and you can do a very simple. Pioneer was a mathematician who has developed this technique, and by which one can. Some of my students, see, even when I was teaching to space dynamics, my undergraduate students published paper, at least 20 through 30, 25 research papers were published during my time when I was there. Because these can be done. They do this project for 4 months. So 4 months only we can give them simple problems. So these are all computational. So you do computational, you find out those things, and then you see what new things you have found out. Write a paper and publish it. Next, another problem which our Earth will faces is always from the asteroids. Between the orbit of Mars and Jupiter, there are innumerable millions or millions of these small bodies are also rotating about Sun. And many times it so happens, because of the large gravity of Jupiter, they change their path and they come towards Earth. So you can see, if you see the news, somebody will pass around Earth. But uh, we do not know when anything can hit us. So people are making technologies so that if anything tries to hit Earth, they try to divert the path on this on their way. But that's a very difficult thing. But they can sometimes do also. Technologies are powerful now. Next, these are all from Mangalyaan images. Next, yeah, orbiter mission, south polar ice cap. Next, okay, next. I'm closing. Next. Next. Yeah, this is important thing. Very interesting is Pluto has one moon whose distance is only 19,000 kilometer, and its mass is more than 1/10 of the mass of this. Very rare. This is the only system we have seen in the solar system where L4, L5 are also unstable. Next. Okay, we can now. You go quickly. If I have anything, I will explain. GSLV. Otherwise, we'll close it. Mostly, I have told you. Okay. So, thank you very much.
Okay, that was a very enlightening session. Dear audience, now we open the floor to any questions and doubts you may have regarding the presentation given by our honorable chief guest, or if there's any information that you wish to gain from the vast wealth of knowledge that he possesses.
Yes, friends, any question?
Any question whatsoever.
Yes, sir. Yes, sir. You can ask the question.
Sir, we just want to know that if any student wish to go for this area, space research, then how we can do it? Which are the institutes after the graduation, what we can do?
See, after you do graduation, you have to do post graduation.
It is the best.
Let me add to this, sir. So, is there any book which you think that is important that every subject in this field should study? You can call him like that in the book in analysis, principles of mathematical analysis by routine that is called the baby routine, which is also known as the Bible of that subject. Similarly, in Euclidean geometry, there is a book Elements by Euclid that is also known as Bible of that subject. So, which book the students should keep with them to do research in this field? Any?
Actually, there are many books in this area, but every book, which written, it is related to mostly uh, to the expertise of the author. So no book as it is I see, which covers vast areas. So one book may be difficult where you can get lot of information. In my opinion, I think a few books, but some books are, I think, available free also. They are, but I can give those who are interested. I can whatever I have soft copies I can give.
So we had already in the previous years we had mechanics as one of the papers, statics and dynamics, which is not there now. I think it will be in the NEP system now in advanced mechanics, so that they can go for that book. I think mechanics is necessary. Any book on mechanics is necessary for this.
Yeah, mechanics is actually important. If you know mechanics, then it is easy to understand. See, when I was a student here, Delhi University was very strong in applied mathematics. See, because we studied dynamics, we studied all Hamiltonian and all those things in MSc, and in BSc honors, 8 papers. 2 papers were one paper was statics, dynamics, and dynamics, statics, and hydrostatics, and one was advanced dynamics. So they were very useful. I think I got a very good background from Delhi University to enter into this area, and also at that time numerical analysis was not very common. Now it is very common. Many places people teach. But Ramjas College, our principal said we should teach something new. So he introduced numerical analysis. Teacher was not there. Then Professor M.K. Singhal, he came from, because he was a student from Ramjas College. So he learned numerical analysis, and he taught us partially, and partially one of our other teacher, Dr. Rastogi, he taught us. So, but numerical analysis was very useful, because with numerical analysis, this subject needs numerical calculations quite a lot. So that way, I got and other colleges were teaching statistics. In our college also, it was to be taught statistics or this numerical analysis. But he said, no, we'll teach numerical analysis. That time it was new, but now it is very common. All engineering colleges, numerical analysis is compulsory. Because without numerical analysis, engineering fellows cannot do calculations. A lot of things are taught. So that way I got a very strong background for doing space dynamics. And space dynamics was also taught as a special subject in MSc. Now it is not there. Gradually, Delhi University has become weak in applied mathematics, strong in pure mathematics. Maybe some people thought applied mathematics is not a mathematics, but that is a thought. So, but I was lucky when I was studying. I got both. We got pure mathematics and applied mathematics. Both we got, because we got function analysis, and then topology was optional. So MSc topology was optional, but this metric spaces was compulsory, and some area some 2 papers. MSc previous 2 papers were pure mathematics, 2 papers were applied mathematics, compulsory. Final 2 papers were one was fluid mechanics, for example, was compulsory, but function analysis were also compulsory, but 2 were optional. So that way, you see, you have a choice. Whether you go towards applied mathematics or you go for pure mathematics. So I chose space dynamics and ballistics my options. So I got all the necessary requirement for it. Any other question? Please come. बहुत बड़ा प्रॉब्लम है। ऐसा है कि अब दिल्ली में पूछे हम कि भाई ये इतना बड़ा वो है, इतनी सारी जो ट्रैफिक जाम होते हैं, तो क्या कर पाती है गवर्नमेंट? कर पाती है कुछ? कभी कभी तो हम सुनते हैं कि 2-3 घंटे तक हो गया, मतलब वो गुड़गांव से लोग आ रहे हैं, दिल्ली तक आ ही नहीं पा रहे। तो एक्चुअली क्या है कि वहाँ उनके पाथ तो हैं, यहाँ तो ये कि भाई एक ही जगह रुके, वहाँ रुकते नहीं है, सब जा रहे हैं ऑर्बिट में। उसका ये है कि उसमें सबसे बड़ी दिक्कत ये है कि जब हम लॉन्च करते हैं तो अगर किसी से हिट हो गया तो दिक्कत है। अब कोशिश ये कर रहे हैं लोग कि कैसे उसको कम करी जाए, बहुत सारे मेथड ढूंढ रहे हैं, दे आर सर्चिंग सम न्यू मेथड्स। पर ये है ना कि अगर उसको किल किया, मान लिया हिट किया, तो और बन जाएंगे डेब्रिस। जैसे चाइना ने अपने वाले को हिट किया तो एक से पता कितने बने, वो लाखों में बन गए थे, छोटे छोटे, और हजारों में तो बड़े बड़े भी बन गए थे। That's a very, very costly thing. So people are trying their level best to find out new methods. पर अभी I'm not sure कि some solutions are being coming. जब उसका एक मेथड ये वो कर रहे हैं कि जब आपका सैटेलाइट अपर एटमॉस्फेयर में 36,000 पे अगर वो है, जब वो आपका लाइफ खत्म होने वाला, कुछ रखें फ्यूल, उसको थोड़ा और ऊपर पहुंचा दें, फिर भी वो वही रहेगा। हाँ, बट इट विल नॉट मेक डिसएडवांटेज टू अदर फंड्स। दे हैव फाउंड 300 किलोमीटर। एनवायरमेंट तो पॉल्यूशन ही रहेगा वहाँ एट दैट लेवल। यहाँ क्या है, सी आई वन थिंग आई टेल यू, जो नियर अर्थ में है, all the satellites which are below 600 kilometer, one day or other day they will come. Only it's a matter of time. Some may take 2 years, some may take 3 years, some may take 4 years, 5 years, or 10 years. But they gradually, because of atmosphere, friction. See, atmosphere is there. When they are passing, friction is because of friction they lose energy. So gradually they will be coming down, and they will ultimately they burn, and they don't do any damage to others. At 78 kilometer altitude, they burn violently, and nothing comes on Earth. But the problem is those which are around 1,000 kilometers, and there only the more important satellites are to be launched. If they hit each other, there is a problem. The problem there is hitting each other. See, on here we are able to, on Earth we are able to, okay, still when vehicles are going, we are able to avoid hitting. But supposing people are driving rash, then people may hit each other. तो वहाँ तो फिक्स है, एक बार आप जो भेजा, इट हैज गॉट इट फिक्स पाथ, वो वहीं रहेगा। थोड़ा बहुत चेंज होगा बिकॉज ऑफ द अदर फोर्सेस, बट इट विल रिमेन देयर। तो प्रॉब्लम यहाँ वहाँ उसकी नहीं है, उसकी प्रॉब्लम वहाँ है कि वो अब उसको वहाँ से लाएंगे कैसे। लोग सोच रहे हैं कि उसको पकड़ लें और उसको ले आए यहाँ, ऐसी बहुत सारी तरकीबें सोच रहे हैं, पर अभी मुझे नहीं लग रहा कि अभी इतना आसान, क्योंकि बहुत एक्सपेंसिव है, बहुत ही ज़्यादा एक्सपेंसिव। बट पीपल आर ट्राइंग देयर लेवल बेस्ट कि इट्स ए वेरी हॉट टॉपिक इन द वर्ल्ड, हाउ टू रिड्यूस, अदरवाइज वन डे पीपल विल नॉट बी एबल टू लॉन्च सैटेलाइट्स। वो कहीं होगा उनका, आपने 200 करोड़ खर्च किया सैटेलाइट लॉन्च करने में, बहुत महंगे होते हैं, और आपका सैटेलाइट हिट कर गया तो आपके 200 करोड़ तो गए। ये सब प्रॉब्लम है अभी फ्यूचर के लिए, है बहुत सारी प्रॉब्लम, वेरी बिग प्रॉब्लम। दैट्स व्हाई आई रोट ए डॉक्यूमेंट ऑन स्पेस ड्यूरेशन, बिकॉज अवर पीपल हु विल कम एटलीस्ट दे विल नो व्हाट वर्क वी हैव डन नाउ, so that when they go further, after reading they will know, okay, these are all problems available, how to solve them, something they can go further. With that aim only we were, and all three of us are very senior people. My boss is actually one of the best in the ISR. He is got a Padma Shri also for his research and for his development. All Mars mission, every mission he was involved. All missions, still he is there. He is around for 4 years, around 4 years elder to me, 3-4 years. but still he is active. Every day he goes to office works.
Yes, sir. Thank you so much, sir, for answering all these questions.
Okay. So moving forward, I would like to request Govind sir and Pooja Koda ma'am to present a memento as a token of our appreciation to our respected guests.
Thank you, sir. To bring this enlightening session to a close, I invite Binay sir to give a vote of thanks to the respective guests and everyone present here.
Good morning, everyone. It is my privilege to present a formal vote of thanks. We are extremely thankful to Professor R.K. Sharma and Mrs. Madhu Sharma, ma'am, for providing their valuable time out of their busiest schedule today. Sir, we all enjoyed your talk and updated our knowledge about the space program of our nation. I am sure that the student will be benefited a lot from your lecture, especially those who are interested in celestial mechanics. Sir, once again, thank you so much. I am thankful to our principal, Professor Arunatri, for his overall support. I am also thankful to respected faculty members of mathematics and other departments. I am also thankful to senior retired colleagues, Dr. Kulan Sharma, for their valuable guidance and support. I am thankful to TIC Dr. Pujaram Verma for taking initiative to organize such a wonderful lecture. I am thankful to all the staff members of college and my dear students for their support. Thank you all.
Thank you, sir. Before we conclude, I kindly request everyone to rise for the national anthem. Everyone, please sit down, and we want all the faculty members and Professor R.K. Sharma to take a group photo. I also want to invite everyone present here around the stage so that we can also take a group photo there. But before that, I want to thank everyone for gracing us with your presence and for being a beacon of knowledge and inspiration. We wish you continued success in all your future endeavors on behalf of the administration and staff. Thank you, everyone. I want the core members and organizing members to stay here in this particular room.